This modern physics lecture is on wave-particle duality. I'm Mrs. Esta. Let's get started. Wave-particle duality is a theory that physicists have presented that represents light and tiny particles as behaving as both a wave and a particle. We know that light can be represented as an electromagnetic wave. So if we envision light as a wave, it has oscillating electric and magnetic fields perpendicular to each other, moving like a wave, where a wave transmits energy without transmitting mass. We can think of light as a wave in some situations, but in other situations, we have to think of light as a particle. A particle will transmit energy and mass simultaneously. We call a particle of light a photon, where a photon is represented as a tiny massless particle that travels at the speed of light. So, how is it that we came to this conclusion that light can be treated as both a wave and a particle? Well, the answer is, it really depends on the scale at which you look at light. When we get down to the teeny tiny quantum scale, things start to get weird. So let's take a journey from the beginning and get down to a small scale to understand this wave-particle duality. So, physicists for a long time have wondered, what is light? Is light a wave or a particle? Well, in order to understand this, we looked at some of the properties of both waves and particles. We couldn't figure it out based on reflection, well, because particles can reflect. Imagine throwing a tennis ball off a wall. It bounces off the wall and reflects back to you. So particles can reflect, and waves can reflect as well. You know this every time you look in the mirror in the morning, or if you hear an echo of a sound wave bouncing off of a building. We know that waves can reflect as well. So this didn't shed any light on the argument. Is light a wave or a particle? Reflection can't reveal the answer to us. So physicists had to continue looking. We looked at a property called refraction. Can refraction tell us whether light is a particle or a wave? Well, it can't. Particles can refract. If you threw a ball, let's say from air into water, like you threw a ball into a pool or a pond, when that ball hits the water, it's going to slow down and change directions. So in that way, a particle can refract. We also know that waves can refract. When water waves bend as they travel from deeper to shallow water, let's say an ocean wave, we know that they slow down and bend as well. So refraction wasn't the answer. Refraction happens with both particles and waves, so that can't tell us if light is a particle or a wave, because it can do both. We needed something that showed us that light can only do one of these things. So if both particles and waves can both reflect and refract, what is light? The question still remained unanswered. We needed some evidence that pointed clearly to one side or the other. Is light a particle or is it a wave? The experiment that shed some light, on the situation came in the early 1800s with Thomas Young's famous double slit experiment. The experiment involved shining sunlight through two tiny openings, so two slits where light could pass through. He then observed on the screen behind those two slits the pattern that was created. If light behaved like particles, you would expect two clumps of light particles to hit the screen behind it as if you were throwing tiny little particles through those two open slits. But that is not what he found. He observed an interference pattern on the back screen with alternating bright and dark spots. This interference pattern was proof that light was behaving like a wave, because waves can interfere, but particles cannot. Those bright and dark spots were evidence of both constructive and destructive interference. Constructive interference are areas of big amplitude waves, and destructive interference are areas of low amplitude waves. So this happened when two waves combined together and put together their amplitudes. Because interference is a behavior of waves and not particles, physicists finally had evidence pointing them in one direction. Since waves can interfere, but particles cannot, that means that light looks like it is a wave. So we're finally answering the question, is light a particle or a wave? And in addition to the evidence of interference, physicists also found that light can diffract. We saw this a few weeks ago with our diffraction glasses when we looked at white light and it became that rainbow of colors. And we also looked at an example of polarization with the two lenses. You can polarize light and organize it to vibrate in a single direction. Well, if light can reflect, refract, interfere, diffract, and be polarized, it must be a wave. Particles can't interfere, diffract, or be polarized. So all of the mounting evidence pointed to light behaving like a wave and not a particle. And this is the model that we followed for the next 100 years until a very famous physicist came along and things got weirder and more complicated. That physicist was Albert Einstein. In the early 1900s, Einstein was able to explain the photoelectric effect with a theory that could only be explained if you treated light like a particle instead of a wave. So this was the first time we had evidence of light behaving like a particle and not a wave, which really confused physicists for a long time. Well, what is the photoelectric effect? Well, we knew if we took UV light, ultraviolet radiation, and you shine that radiation on a piece of metal, it will begin to spark. What's happening there is it's emitting electrons. So that radiation gets absorbed by the atoms in the metal and it emits light or sparks in the form of electrons. Each particle of light, called a photon, contains a fixed amount of energy or quantum that depends on the light's frequency. So the genius of Einstein's theory with his photoelectric effect was he was able to relate a photon's energy to its frequency. And he was also able to relate its momentum to its wavelength. And this was the behavior of particles, not waves. Waves couldn't do this, but particles could. Einstein's theory involved light acting like a particle that had both kinetic energy and momentum. Einstein proposed that a photon penetrates the metal as a particle and transfers its energy to an electron within that metal to knock it out of the metal. The electron, with its newfound kinetic energy, moves through the metal at a high speed until it's emitted from the material. This was what Einstein won his Nobel Prize for in 1921, for his explanation of the photoelectric effect with his particle theory of light involving photons. So now, what do we do? We have evidence of light behaving like a wave, but we also have evidence of light behaving like a particle. What do we do? Well, let's just say it's both. The modern physics view is that light behaves as both a particle and a wave. This is where wave-particle duality comes from. Dual meaning both. And whether it behaves like a wave or a particle really depends on your sense of scale. If all objects are either particles or waves, we get this wave-particle duality when we look at the small scale and the scale of quantum mechanics. So when we look at any small thing like photons or electrons, any teeny tiny bit of matter, including quarks and leptons, anything on the Standard Model, we say that these tiny particles on the small quantum level exhibit a dual-like property where they can either be particles or waves. And again, this only happens on the small scale. So these rules that the quantum particles follow aren't the same rules that we follow in our everyday life, which makes it a little strange, but that's physics for you.